a good reminder to fill in the survey. Please do that. It makes, make a lot of difference to whether we can follow this project up. So where we were at we're just doing a continuation today of the electrostatic energy. We got a bit behind with the lecture on Friday. So I'm going to do electrostatic energy for the whole of this lecture. And because it's a split lecture, this is just a reminder of what we were doing last time. And the idea, very straightforward one, that if we've got 2 point charges, then let's say this is the field created. If you like, this is the potential field created by charge 1, and we can identify this with the electric potential function. We're back in the world where we've got no dynamic effects, just electrostatic, so we can define the scalar potential phi. And of course, if you have 2 charges, it's incredibly easy. You've just got the potential created by charge 1. You bring charge 2 into that field, and the work done is equal to Q2 times phi. Now again, it's extremely simple to generalize for n-point charges. And again, I mentioned this last time, that because we've got superposition of fields and therefore superposition of potentials, once you can pick any charge in a bunch of charges as Qi, call the other one Qj, and of course there's a well-defined distance Rij between them in this static approximation, and all you've got to do is this is the interaction energy between 2 charges, is just sum up all of the pairs of charges. And if you want to do that in a slightly neater way, it's much easier to just run the index from I is 1 to j is 1. But if you do that, you've got to remember to add this factor half. You don't want to count charge Q2 interacting with charge Q3 as an extra interaction to charge Q3 interacting with Q2. So to avoid the double counting, you have this factor of a half. And again, we'll come to this towards the end of the lecture. This summation I is not equal to j. You can't, if you like, put a point charge on top of itself. And we'll come back to that quite quickly. So that was the idea of point charges and the energy of interaction between them. And towards the end of the lecture, I just introduced this problem of having a spherical ball of charge. And again here, we're looking at a uniform sphere of charge. So we want to assemble a ball of charge with a uniform charge density rho. Now, as is usual in here, because of the lack of blackboard space, I'm just going to run through. These are exactly the lecture notes that are on the VLE, and rather than try and write and rub them off all the time, I'm going to run through them. It's up to you if you want to take notes as we go along, but I'm just going to go through the VLE notes. So the first idea is, well, we generalize this formula by saying that the infinitesimal amount of work done in bringing up a small additional shell of charge to the charge shell that already exists must be given by this differential expression here. So the concept behind the calculation is the principle of virtual work, which we can use with a conservative field and a well-defined scalar potential. So we imagine we've already assembled a sphere of radius r, and obviously then the sphere of radius r has got a charge 4/3 pi r cubed rho. Remember, it's rho that's the constant. We're creating a constant surface charge density, so that's what we're going to hold constant when we do the integration. And then likewise, we imagine that we've made an additional shell, and then we've got 4 pi r squared dr is the volume of this little additional shell that we've added by bringing up charge from infinity. So when you combine these ideas, you've got your Q of r in this expression for the work done is the rho times 4/3 pi r cubed. The additional charge we bring up is, again, it's got this constant charge density in a shell of volume 4 pi r squared dr. So all we've got to do is substitute these two expressions into this one to get an expression for the differential amount of energy. So, as I say again, it's I know it goes a bit quickly if you want to take, full notes as you're going along, but it's a very straightforward idea that we're just bringing up extra charge to the charge of radius r and substituting in for these two expressions q of r and dq. So that's the first one. The result of performing that substitution is given in the top line there. So the total energy, of course, we have now to integrate this expression from r equals 0 to r equals a, which is the final volume of the sphere. So in the end, we start off with r equals 0, and we gradually build the charge up as these series of shells until we've reached the fixed radius a of the ball of charge. And everything in this expression, of course, is constant here. The rho is constant, and we've got 4 pi over 3 epsilon naught. All we've got to do is integrate r to the 4th dr, and of course that's a fifth r to the 5th, and we take that between the limits naught and a. We just, of course, the lower limit gives us nothing, and the upper limit gives us a to the 5th over 5. So combining with this expression, we get the total energy of the ball in this way. Now again, having done that, we had to hold rho constant while we were doing the integration. R, of course, is emphatically not a constant. We're integrating the ball from the centre to its fixed radius. So it's more usual, having done the integration, to re-express rho in terms of the total charge q on the sphere. So obviously we can replace the rho squared in this expression using this relationship, and this is what we get finally, is 3/5 the total charge squared over 4 pi epsilon naught. And like I was saying last time, it's sort of intuitively obvious that somehow, because we're in effect summing over pairs of interactions between little volume elements within the sphere, that we're going to end up with something that goes as q squared and something that goes as 1 over a. And when you do the calculation, the prefactor is 3/5. So again, you could interpret this. You see, if you want to go back to this idea of charges interacting with each other, if you compare that with our general expression, basically what you're saying is that if you average 1 over rij for all pairs of points within the sphere, you get 3 over 5a. And I say that seems quite reasonable, because in the end, if you consider, well, here's a bit of charge and it's interacting with a bit of charge here and a bit of charge here, that you would expect that the average distance of one charge to another is going to be of the order of a, and it turns out to be 5/3 a. So you can interpret this result, although we've done it by integration over a continuous charge, you can sort of imagine, if you want to map it onto the result for the point charges, that you've got an average over 1 over rij is just equal to 3 over 5a. One of the things that is noticeable about this is that if a goes to 0, in other words, if you shrink your ball of charge to a point, then the energy goes to infinity. And this is a major problem with classical electrodynamics. You can't get away from it. It's a real problem, and we'll come back to it in a bit more detail at the end. So this is the, if you like, an informal method. We've used the principle of virtual work to obtain this result. So having done that, I want to now introduce the sort of more formal way of handling continuous charge distributions. And it looks ferocious at first, oh my God, a double integral over all space. But again, all that we're doing, if you compare with u is equal to a half the sum over I, the sum over j, of all of the qi, qj over 4 pi epsilon naught rij, well, if you've got a continuous charge distribution, then your qi gets replaced, if you like, by dv1 rho 1. That is the amount of charge at the point 1. Your qj gets replaced by dv2 rho 2. That's the amount of charge at point 2, and of course your 1 over 4 pi epsilon naught and your prefactor of a half get carried down. And now R12, because we're integrating over distributions, we tend to use the Roman numbers rather than letters. This Rij just becomes R12. So if you like now, you reinterpret this formula that when you do the integration over dV2, this is effectively just saying, well, that is the potential produced by the charges in the volume elements dV2. So this whole integral over dV2 rho 2 over 4 pi epsilon naught R12 is just, together, the potential at point 1 created by all the charges at point 2. And so if you take that out, all that you're left with, again, we've got the factor half in the front, we've got rho 1 dV1, and then this whole rest of this thing here just becomes the potential at point 1. And again, once you've got it to this stage, well, point 2 no longer appears. You've already integrated out the volume integration over the charge density at point 2. So you don't even need now to put in a subscript here, because you're just performing an integration over the volume of the potential times the charge at that point. So if you like, again, I'll make 1 or 2 board notes as we go along, because this is the general formula. So the general formula for continuous charge distributions is a very, very simple one. Let's say when it's written out in full as a double integral, it looks rather ferocious, but in the end it's just a half times rho phi dV. And to keep it, obviously the equation numbers here, I'm going to miss out a lot of the stuff that's on the VLE notes, but that on the VLE notes, that's equation 2210. So this is the general formula. Now, a lot of people now go to a great deal of trouble to prove that this equation here, which is the general equation, is the same as this equation here, where you've got epsilon naught over 2 integral over all space of E dot E dV. So this is the previous lecturer's notes from this course, and this is the formal proof that this is the case. So you don't need to know this, but I just thought, again, for the more mathematically keen students, again, it's not very nice to just say, oh, well, this somehow leads to this, because you can clearly see if you've got an integral of this type, the previous lecturer used Tor for volume integral, but it's the same as my dV, integral over all space. Well, of course, this is one of the Maxwell equations. It's always true. So we can clearly replace our rho by epsilon naught times del dot E. And because that's a fundamental constant, we just take it in the front. So under the integral, you've got the divergence of E times the potential at that point. And again, you might have done this with Peter Main's course, that if you have any scalar field P and any vector field A, you can use the general theorem that the divergence of PA is equal to P times the divergence of A times the gradient, A dotted with the gradient of P. Of course, this is a scalar quantity on both sides of the equation. This is the gradient of the scalar field, and of course dotted with the vector field again gives us a scalar. So with that substitution, you've manipulated to this form, you use this vector identity, you can now write what's under the integral sign as the divergence of phi E minus E dotted with the divergence of phi. But precisely E dotted with the divergence, the gradient of phi is precisely, we've used this relationship throughout, that the electric field is the negative gradient of the potential. So this term here gives us the epsilon naught over 2 times the volume integral of E dot E. This is converted by the divergence theorem. So this is a volume integral of a divergence. We can convert it to a surface integral of this field. Again, the previous lecturer used S for surface, and I've used A. But this is the same idea. And then when you take the surface integral, we're again using this result, and I've mentioned before that you've got to be a bit careful with where you choose the zero. So we're choosing the zero of potential to be at infinity. So this integral is zero. This is a trick you'll have used in quantum mechanics quite a lot. So all that it comes down to is this term, which gives you this final result. Now I put that up. It is the... Yes, you go. Where would rock and roll be without feedback? How's that? Better? Yeah? So you can convert this general expression into this other general expression. And this is a crucial step. It doesn't seem like we've done much at the moment. It looks formal. But this integral is equal to U is equal to epsilon naught over 2 E dot E dV. So that's the formal proof that this expression and this expression are identical, and it's just manipulations in vector integral calculus that give you that. So it's just written in the VLE notes as we can show that equation 2210 is numerically equal to equation 2211. So this one was 2211 in the notes. Now it doesn't look as if we've done a great deal. Of course, however, we can always take the epsilon naught over 2 if we like inside the integral. But the point now is if this is the total energy, which is obtained by a volume integral of this thing, then this must represent the energy density in joules per cubic metre at each point in space. Our integral over dV, of course, is going to give us something in metres cubed, and this quantity here clearly has the units of joules per cubic metre, because this is the total energy in joules of the system. So this is a crucial point, that you interpret this equation as saying that when you've got an electric field, there is located in space an energy whose density is lowercase u. And again, you know, people who write textbooks aren't setting them up for lectures, they're setting them up for people who are just reading. And so there's absolutely no ambiguity in a textbook, because a lowercase u doesn't look like an uppercase u. I've decided not to rename it by some other letter, because this is the way you'll see it in all the textbooks, including Feynman. So we identify this, we interpret the expression as shown in figure 98. So in other words, we've got some electric field which just exists. It can have any shape, any form. But the idea is that if we take any little infinitesimal cube in space, any one of these volume elements contains an energy E squared times epsilon naught over 2 dV. So we've now got, again, and this is like the more advanced formulation of electrostatic energy. Again, we've now defined the energy as a function in 3 dimensions. We've got an energy density that exists everywhere in space, and we integrate over that to get a total energy. And so this is a very big step forward, is that then so again, I'll use this board, just go to this side for a moment. We can therefore define an energy density U, and this is, again, I'll just emphasize, just this one time, lowercase u, very easy to confuse the energy density with the total energy because they're both written in U. And energy density U given by U is equal to a half epsilon naught E dot E, or of course if we prefer we can E dot E is just E squared, so we can write this as a half epsilon naught E squared. And this is the other major, if you would like, general expression that we need. Nobody's succeeded in the unified field theory yet. One of you is going to do it, of course, inspired by this lecture course. But you'll understand that this is a different sort of level of looking at electrostatic energy, because energy, we know, well, for example, Einstein's 1911 paper, bending of light rays going around the sun, of course, light is a form of energy, and it's attracted by a gravitational field. So, in the end, you've got to know where the energy is in order to have a completely general theory of physics, because this energy at any point will have gravitational effects. And you see, now we can say where the energy is. This is very different. You know, if you start off just with the kind of, oh, U just due to two charges, U1, 2 is Qi, Qj over 4 pi epsilon naught Rij, well, that correctly gives you the total energy of 2-point charges. But, you know, where's the energy? Is it near charge 1? Is it near charge 2? Is it halfway between them? Is it, you know, somewhere over in Alpha Centauri? This tells you where it is because you know the electric field as a function of space, so you know the energy density as a function in space. Now, to give you confidence in that new result, the next calculation, I did a couple of example calculations. Example 1 was the, you know, like when we did the ionic lattice using the point charges. Example 2 was that example of a ball of charge. Example 3 is the energy of a capacitor. And you probably think, oh my God, you know, did that to death with Kieran last year. But that's the point, is that you know the answer. So I want to show you how you get the same answer from this new formula, 2212. Well, again, we're going to do all the usual physics tricks, which is, first of all, we are going to ignore any edge effects in the capacitor. Of course, we know in a real capacitor, the field lines will be quite complicated around the edge. We've got a load of positive charges here and negatives here, and the field lines don't really stop suddenly at the edge of the capacitor. But we do the typical physicist approximation. We say, well, we're going to just calculate in this region here and assume it's, if you like, an infinite parallel plate capacitor, so that the field in between the plates is completely uniform. So we know it's entirely straightforward that you've done this before. One of the reasons you often use the parallel plate capacitor for examples is that the electric field just points from one plate to another. This is in volts per meter. It's a uniform field. This is in volts. This is in meters, where d is the distance between the plates. So immediately, the energy density in the capacitor is a half epsilon naught E squared, just becomes a half epsilon naught V squared D squared. Now, the volume of the capacitor is just the area of the plates times the distance between them. We've got a beautiful rectangular type of system. So again, A is the area of the plates, D is their separation. And because the energy density is completely uniform, although strictly speaking, we now have to integrate it over all space. Because it's the same everywhere inside the capacitor, all we've got to do is multiply by the volume in order to perform the volume integration. So the total energy is this energy density U, which is a very straightforward expression in a capacitor, times the volume V, which is just the area times the distance. So again, that's extremely straightforward, just to write that in a single line, and then you get the expression a half epsilon naught over A over D times V squared. But now we know, and this is something you'd have done to death with Kieran last year, this is the reference to the Young and Friedman book. where it's proved, this is the capacitance. So again, I've brought, just to remind you, again, because I obviously want to make this, this proof as convincing as possible. Well, of course, Gauss's flux law gives you the charge per unit area, sigma over epsilon naught as the field, but the sigma is just Q over A. We've already been using this relationship that the voltage drop is the integral of the electric field is ED. We've already used it in the form E is equal to V over D. So with this expression, you've got V over D on this side is Q over epsilon naught A, and just a simple algebraic rearrangement gives you the charge as equal to epsilon naught A over D times V. But by definition, that's how we define capacitance, that Q is equal to CV. So clearly, for a parallel plate capacitor, we have this expression for C, which is epsilon naught A over D. And once you've got that expression, again, it's, I've included that to be thorough, then this expression here, where we've got the total energy, we can identify this with C, and so of course U is a half CV squared. And of course you knew that result from the outset, but this would show you, this is how to obtain that result using this formula. And in the end, as I say, it's a very straightforward manipulation. And again, some people rearrange it, and indeed in one of this week's problems, I've asked you to obtain that by the principle of virtual work, which is something that you did in the lectures with Kieran last time. So that gives you the energy of a capacitor using this new way of thinking. Example 4 is bringing you now to a fundamental problem in physics, because you've got to bear in mind that now this formula, it doesn't say anything at all, this way of looking at it, about interactions between charges. This says if you've got an electric field that exists anywhere in space, that field has got an energy density. So this is a single charge on its own now has energy. Because a single charge, we know, if I've got a point charge Q, it produces a radial electric field of Q times over 4 pi epsilon naught r squared. And I can certainly take E squared of this field and calculate the energy density of a point charge. And so the total energy of a single point charge will be obtained by integrating that expression over all space. So again, this is, if you like, I've just popped this in for sake of completion here as equation 2213 on the notes, to see, well, where does that lead us? We know now that a single point charge Q has got this amount of electrostatic energy. So we know, let me just sift my way through here, usual view graph shuffling maneuver, that if we take this expression and we substitute it into our expression for energy density, well, of course, we just square the electric field, which gives us the Q squared over 16 pi squared epsilon naught squared r to the 4th. We then multiply by epsilon naught over 2, and we get equation 2214. So this is the energy density that's just being produced by a single point charge, with no reference to anything else, any test charge we bring up into the field. So again, we take as the volume element, as usual, this spherical shell of volume 4 pi r squared dr, and the total energy, capital U, again, this is the capital U, this is now obtained by we know the field is spherically symmetric, so our two angular integrals, if you like, just bring us down the factor 4 pi, and then we've got the r squared dr integral of this expression. Well, of taking all the constants together out the front, the essential integral, we've got an r squared here, and r to the 4th here, because of course when we square our electric field of a single charge, we've got a 1 over r to the 4th dependence. We've got to integrate from 0 to infinity 1 over r squared dr. Well, couldn't be a much easier integral. increase the power by 1, get r to the minus 1, divide by the new power. We have minus 1 over r between 0 and infinity. And the problem with that result is immediately apparent, that from the lower limit, where the radius is equal to 0, we've got a 1 over 0. So if you have a single point charge and you follow through the classical theory, then it has an infinite amount of energy. And so this is, if you like, the final note on the VLE lecture notes. We must conclude the idea of locating energy in the field is inconsistent with the assumption of the existence of point charges. And it was precisely this sort of problem that led Feynman, Tominaga and Schwinger and other workers to quantum electrodynamics. And again, quantum field theory, quantum electrodynamics is beyond what we're doing. I've stressed throughout the course it's a classical field theory, but also to note it's not internally consistent with what we've done, because in the end the Maxwell equations don't say anything about point charges. So the problem is actually with the concept of a point charge rather than with the concept of field energy. I mean, when you go back to the original set of Maxwell equations, you don't see Q1 or Q2. No point charges appear. The only way that charges appear is as a smeared out charge density in coulombs per cubic meter, or indeed in magnetic effects as a smeared out current density in coulombs per square meter per second, or amps per square meter. So, and Maxwell was aware of this kind of problem, that if you have point charges, you end up with severe problems with the called divergences of classical theory. Now, this is we can't brush it under the carpet. This is a fundamental difficulty in our understanding of physics, and it's puzzled physicists for a long time, and it still does. Of course, you can get the idea, of course, in quantum electrodynamics, an electron is going to be described as a wave, and, maybe a fairly localized wave, but a localized wave. So if you like, your probability density of finding an electron is probably, got some kind of wave-like character, and even if the wave attenuates quite rapidly, that's very different from having a delta function in position. A point particle, it's there, it's at this position. This could be some distance variable, and of course it's more difficult to solve those problems, which is exactly why they're left to the kind of fourth year maths course. So I want to develop this idea of the a little bit further. So first of all, here's a kind of like a bit of a summary, because I made, well, obviously my jokes aren't very funny, they're physicist jokes, but I made the joke earlier in the course that when you come into university physics, you've learned Coulomb's law, and that it works. This is true in static situations, and the corresponding formula for energy to the Coulomb's law force is, of course, this one that we dealt with in the lecture last time. And then you're going on now to a more sophisticated way of looking at electrostatics. You rewrite Coulomb's law in the form of Gauss's flux law, that the surface integral of the electric field is the volume integral of rho over epsilon naught integrated over the volume. And the comparable degree of sophistication for the energy formula is that you've got a half rho psi dV, which is the formula on that board there. But the sophisticated way of doing it, if you want to really get there quickly, is the differential form. And this is an equation which is true at every point in space. So something I've emphasized throughout the course, the Maxwell equations are differential equations true at every point in space. And so the corresponding concept is to use the energy density, which is defined at every point in space, and that is the formula. And again, there's a much deeper reason. It's not just, this is sort of more elegant and whatever. There's a very important reason for using this new concept, because this equation is also true in electrodynamics. This is, and we'll apply it to, if you like, light rays next week. So this holds even if you've got a very rapidly oscillating field and also magnetic effects, whereas clearly this equation emphatically can't hold in electrodynamics because you can't define an scalar electric potential function when the charges are moving. So when you go to electrodynamics, and I mentioned right from the outset, Coulomb's law is not true when the charges are moving, it's only static. So we have to, in the end, in electrodynamics, go away from this formula and go away from this formula and use this one. And that's precisely what we'll do next week. However, what I'd like to do next is to show you an example of how, and again, this is on the VLE, of how you can do the electrostatic energy of a ball of charge with this new method. So this is now where the new method reveals its power. When you do the capacitor thing, it's almost like too easy as an example. You think, oh, you know, why bother? Basically go to this very sophisticated new way, because you know perfectly well that all the energy will be uniformly distributed inside the capacitor because the field is uniform, and it's a trivial problem. You know all the energy is inside the capacitor. But where is the energy in a ball of charge? Now you'd think from the first idea, if this was a uniformly charged sphere, that the energy would be inside the ball, because you think, well, all the charges are interacting with each other within the ball, and the energy will somehow be contained within the ball. And so the answer comes as a very big surprise, and that's what I'm going to work through in the next few minutes. So first of all, again, this integral overall space, because we've got a charge ball and the field is always radial, the field, we've got a radial function for the field, the volume integral just becomes 4 pi r squared dr. Again, if you prefer, your two angular integrals bring you down the factor 4 pi, so your r squared sine theta d phi dr is just 4 pi r squared dr. And of course, it's convenient to simply combine this factor, the 4 pi, with the epsilon naught over 2 at the front, and then just take the integral of E dot E r squared dr. So again, you know, if you want to take notes as you go along, it's up to you, but this is available, and it's probably better just to follow the calculation. Now, the electric field inside the ball, so you cast your mind back right to the beginning of term, I set a problem exactly like this on Gauss's flux law. Again, it's a simple application of Gauss's flux law that inside the sphere, this is the surface integral of the normal component of the electric field, and this is the volume integral of the charge density divided by epsilon naught, and that gives you immediately that the electric field is equal to the charge density over 3 epsilon naught times r. So inside the sphere, we have the electric field rising linearly to the surface, and then, as we know, outside, the well-known result that once we're outside, we just get the 1 over r squared decay. And I asked you in that question to prove the field was continuous. In other words, to use this formula on the inside, and the E is the total charge over 4 pi epsilon naught r squared on the outside, and show that they join up at that point. So we know that this field inside is rho over 3 epsilon naught times r. So we just have to substitute that field into this equation. So we can re-express it. Again, always we can use that our Q, the total charge Q, is 4/3 pi rho a cubed, and we get this expression for the electric field squared inside in terms of the total charge on the sphere. So inside the sphere, again, taking all the what we've got to do to get the total energy inside is integrate from 0 to A. We're now starting at the centre of the sphere and integrating outwards to R is A. And of course the only functional dependence is that we've got R squared E squared dr. So again, it's an extremely straightforward integral. And of course, it's not an accident that it's the same integral we did when we did the calculation by using virtual work. We've got an integral of r to the 4th dr with this bunch of constants in the front, where this is the constant radius of the sphere. And of course, this is just r to the 5th over 5. And between those two limits, it's just a to the 5th over 5. So continuing on to the next part of the calculation, that was our prefactor, that was our integral. We get that the energy inside is q squared over 40 pi epsilon naught a. So in other words, the energy inside the sphere is 1/10 times q squared over 4 pi epsilon naught a. So the energy inside the sphere, what we've done, we've taken E, we've squared it, multiplied it by epsilon naught over 2, and integrated it from 0 up to A. That gives us the energy on the inside of the sphere. So that's how the formula works and this is a better example because now the field is not uniform. We really have to do the integral because not like between capacitor plates, the field here is a function of distance from the centre. Outside, well, we've always got that result because once your Gaussian sphere where you do your integral is outside your ball of charge, then always you've got that the the total charge over epsilon naught is the right-hand side of Gauss's law, and that's the field times 4 pi r squared, and so we get this expression for the electric field outside. And again, of course, we can just square that expression to give us this one here. So outside the sphere, of course, I've now got to integrate from A out to infinity. The energy outside the sphere is obtained by integrating the square of the field from the fixed radius up to infinity. And now we've got, again, this integral of r squared dr over the square of the electric field. And we've got this integral of 1 over r squared. But now, of course, our lower limit is A. This is the fixed radius of the ball of charge. So this isn't the same as the integral that gave us the problems with the point charge, because this again, it's the same integral, 1 over r squared, but now the limits are between A and 0. So outside the sphere, we end up with, again, the prefactor just carried over. We have to do this integral. Now, we don't get any problem with the limits now, because 1 over infinity is 0, and subtracting off the lower limit is minus 1 over A. It's just 1 over A. So the energy outside the sphere is this form. And again, I've written it to be more transparent in terms of q squared times 4 pi epsilon naught A with the prefactor. Now, when we combine with the energy inside, we had better get the total energy of the ball of charge. And indeed we do. And adding a half to a tenth, we get 6/10, which is 3/5. So we knew this answer all along because we did it by the principle of virtual work at the beginning. But now we know where the energy is. I mean, we can find the energy at any point if we like, but we've integrated it from the centre of the ball to the surface, and we got this result. We integrated it from the surface out to infinity, and we got this result, and the total gives us the total energy, and we knew, because the principle of virtual work is true when we can define a scalar potential, so of course we have to get the same final result, but at first sight it's rather surprising that there's 5 times as much energy outside the ball as inside. So it's, I mean, you could say crudely the reason is that although the electric field is more intense inside, the ball is quite small. whereas infinity is quite a long way away, and the field continues to have energy as you move outside the ball. But if that's a uniformly charged sphere, there's 5 times as much field energy outside it as inside it. So that's a very, very interesting conclusion. Also, you see too, if you do it this way, again, you kind of think that the energy is going to be inside the ball, because this isn't a volume integral over all regions occupied by charge. And you kind of think, well, that's going to be 0 anywhere outside the ball, because rho is equal to 0. But remember that if you're bringing up a charge from infinity, the potential depends on the whole process of moving the charge from infinity. So it's misleading. Your first reaction is that, you know, what that calculation mine does can't be right, because if we go back from this way of thinking, which we've just used, to this way of thinking, you think, well, wait a minute, rho is 0 anywhere outside the ball, so the integral is 0, and you tend to think the energy's inside, but the potential is not 0. And just as a final piece, I'll try and show you how the formula works in this way, and why there's no problem. So again, if you've got this integral to do, that's the general integral. And again, the sine theta d theta d phi. This just brings me down a factor 4 pi in the front. What I've got to do is integrate r squared rho of r phi of r dr. And of course, the integral now, because the rho of r is only non-zero in the range 0 to a, but the potential is determined by bringing the charge up from infinity into the ball. So you still get effects from outside the ball, as shown in the next one. So if you make this substitution, we can always use either rho or q, because this is just the fixed volume of the ball, so the total charge is its volume times the charge density. So you can always express rho in this way. So if you re-express your integral a half rho phi in terms of the variable rho, the integral is a very straightforward one. And this gives you the total energy as given in this expression. And again, you're only integrating from 0 to a, but this is determined partly by the work done in bringing the charge up from infinity. So if you do that expression, you can always, I mean, again, I don't know whether you did this calculation with Kieran last year. Just like we calculate the electric field goes like this. There's the inside going as rho r over 3 epsilon naught, the outside as 1 over r squared, and of course they are equal at the surface. The potential, you see now, the potential is determined partly by bringing the charge up from infinity to a, and that's the 1 over r squared integral from infinity to a, and partly by bringing the charge from a to r. So this is the correct potential function for the case of a spherical, and again, a lot of people don't bother to calculate the potential, but if you want your potential energy phi to be 0 at infinity, the expression for the potential depends both on moving the charge from infinity to a, and then moving it in, if you like, further towards the centre to this variable distance r. And this is the correct expression for the potential of a sphere of charge. And so now, your final step, you've got to do the integration of that quantity. The old disappearing view graph. Final view graph always disappears. I'm sure it was here somewhere. Take a little nap for a minute now while I just look for my last view graph. And there it is. So again, you know, this There's a lot of maths here. I wouldn't expect you to take notes as you go along, but you've got this expression for the potential. You substitute it into your expression for the energy, and you get your total energy as this integral. When you perform, again, once you've gone through the calculation, the final integrals you have to do are trivial. You've got an r squared integral here, which gives you a third r cubed, and you've got an r to the fourth integral here, which gives you a fifth of r to the fifth. And then when you substitute into this expression, you get u, surprise, surprise, as you go through the calculation, ends up as 3/5 q squared over 4 pi epsilon naught a. It has to. But the reason that I went through that calculation in some detail is because you'll see that although the integral appears to be 0, because this is 0 outside the volume occupied, the potential at the point r is determined partly by bringing the charge up from infinity where there's 0 potential. So that gives us, you know, we've now gone through this method. On Friday, there's a similar formula, just like and I'm not going to derive it. I had this formula epsilon naught over 2 E dot E, and you've seen that the formal proof is actually a little bit hairy. I'm going to call that a subscript E next time, because this is the electric energy, and without proof, I'm going to say that the magnetic energy density is epsilon naught c squared over 2 B dot B, and then we'll take it from there. Okay, we've reached our time. Have fun, and I shall see you on Friday.